Okay, so picking up from yesterday, we started with investigation 14, and our goal is to diagonalize a matrix, but a good reason for why I'd want to do this is just saying why. And here's why. Let's say you've got some matrix A, and it's a 3 by 3, okay? Doesn't matter what your terms are. So maybe it's that. And you want, for whatever reason, doesn't really matter, you want to know A to the 43rd. And you're like, dude, I don't want to do that 43 times. And your calculator's broken. Now, do I understand that your calculator is not probably broken and you can probably just do this? Sure. But if I screw with you and I'm a jerk and all of a sudden I say this is n and this is 3n, things are going to get wild and you're going to be sad. So here's what you do. When we diagonalize a matrix, it is going to be a real quick shortcut for us to be able to do this. So here's the idea. You're going to start with some matrix A. Then you're going to get P, and it is going to be made of the eigenvectors. So like, here's an eigenvector, here's another eigenvector. If it was more than a 2 by 2, then you'd do more than that. Then you're going to get matrix D, which is going to be the eigenvalues down, and notice I kind of color-coded here, so this eigenvector, this eigenvalue, this eigenvector, this eigenvalue, down the diagonals, and this would work for more than a 2 by 2. But then you're going to find that A is equal to P D P inverse, and P inverse, again, fairly simple to do, just you can plug into your calculator, or since your calculator's broken, you can use the P inverse is going to be equal to 1 over AD minus BC, and then DA negative B negative C. Okay. And then, because this is a diagonal matrix, remember how we said that, like, if I just do this squared, it's not like I square every single term, except if it looks like this. In this case, if you square this, so you say D squared, then this really is that. But this is not equal to just squaring every single term. It only works if you actually have a diagonal matrix. So in this case, if I wanted to know A to the 42nd, what I could do is I could say, hey, I know D to the 42nd because I just have to raise every number, every eigenvalue down the diagonal, and then I can multiply it by P and inverse P, and that's 3 multiplications, and this is 42 multiplications, and I'd rather do 3. So that's the idea. So in investigation 14, first thing we did was we found the eigenvalues and we found the eigenvectors. I'm not going to go through that here. We've done that elsewhere, but I will put these notes up. Then what we did was we found P, and that was just the eigenvectors. Then we found D, and that was the eigenvalues. Then we showed that AP is equal to PD. Look at this. They ended up being the exact same thing. Then, and this was fun because this is actually like using this equation we had where you take like the matrix and you multiply it by a vector, and then you get the eigenvalue times the vector. So this is just kind of a fun aside that is actually super useful. But again, AP equal to PD. Then it wants you to show that if this is true, then this has to be true. And I went through and I did some math, so this is definitely true. We already showed that. And then here's what where it gets sweet. If you take AP and multiply by PD, or it's equal to PD, and you multiply both of them by the inverse, you need that inverse of P. This right here is going to be equal to the identity matrix, which just means it's equal to A. So you get that A is equal to P times D times P inverse, which means, and this is what we care about, that A cubed is equal to P times D cubed times P inverse. And here's one way that you guys can see that. A cubed is just A times A times A. This, here we've got 1, 2, 3 of these, but this right here, P inverse times P, that's just going to be the identity matrix. P inverse times P is going to be the identity matrix, and you are left with P, D, 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 P inverse. So you get that this is equal to P d cubed P inverse. Sweet. And then because D is diagonal, we know that D cubed is just like, oh, I probably should put a cubed here, that this is equal to -1 cubed and 8 cubed. Whew, we're getting there. We're getting there, guys. So now we know that anytime we've got D to the n, it's equal to the diagonals raised to the n. And remember, this only works if it's a diagonal matrix. And then, oh my gosh, because we know that a cubed is not equal to this, but I'm too lazy to do this multiplied 3 times. So how do I find it without a calculator? Is this. You'd say P d cubed P inverse. So these are the eigenvectors with their eigenvalues for this matrix. And then this is just the inverse of this matrix. This will equal this. And what's more important, because 3 is really not that exciting, if this was like 31, this is still true. Okay? So the idea is that if you're raising to some ridiculously high power and you don't have a calculator, or you've got some variables in here, eigenvectors, eigenvalues can get you there faster. Your book goes on and gives you an example on page 417. This is example 13. Okay, so we've got a, and we want a to the 4th. I got this from a calculator. So what I did, if you didn't have a calculator or you were too lazy to do this 4 times, you'd find the eigenvectors and the values. Then you set up eigenvector matrix. You set up eigenvalue matrix down the diagonals. You raise it to whatever power you want, and then, le voila, this will be equal to a to the n. Let me know if you have questions.